So, hello. We'll start with the week 7 content today in a few minutes. There's still a few minutes left, so I'll just wait and see if more people want to join, and then we'll start. Okay, so I will start shortly, but before I start, I wanted to check if you have any questions from previous week or this week. Because today's class, in my opinion, is a little important. Although I know most people haven't joined, but unfortunately this week 7 in particular is, I think, the most important part of consumer theory. And most people find this week to be the most tricky, let's say, if not difficult. It's not exactly difficult, but at in your level of study at that level, for example, like mostly you deal with just solving numericals, right? Whereas in week 7, we try to derive the demand function of a consumer, which is not exactly the same thing as, say, solving a numerical, like just plugging in values and getting an answer. So from that standpoint, the weekly sessions are in general important, but week 7 is a little bit more important. So just give me a few minutes to set up the class, and we'll start then. Okay, so let's start. It's kind of past 4 now. So this week we are mostly going to study two things. One is the Marshallian and Hicksian demand functions, and the second thing is income and substitution effects. So both are of course related, as we will very soon find out. But mostly we will first start with the income and substitution effects. Sorry, well, first we'll start with the Marshallian and Hicksian demand, and then we will move on to relating it with income and substitution effects. So there are a few examples of different types which I have taken today for studying in the class. But before I go ahead, I want to first recap how we derive Marshallian demand and how we derive the Hicksian demand function. So I didn't get the time to put it on the lecture slides, but I will take a general case of, when you want to derive, just give me a moment, when you want to derive, say, a Hicksian demand function or a Marshallian demand function. Just 1 minute, give me a moment. Just give me a minute. Until then, for those who have just joined, if you want to ask any question, you can ask me now. Okay, so let's get started. We'll first derive the Marshallian demand, which is generally the more popular, demand function, and then we'll derive the Hicksian demand function for a pretty general case. Say you have a consumer who consumes goods X and Y, and his utility function is given as the simple function U is equal to XY. Okay, and the price of good X is PX, the price of good Y is PY, and say the budget of the consumer is B. So we can write the budget constraint so this is your typical budget constraint equation. This is nothing different from whatever we've done till now. So this is like just how we start. There's nothing new here. All we've done is we've just taken a demand function, we've taken a utility function, and that's pretty much all we've done. Just give me a second. So now if we want to say find the Marshallian demand function, what do we really mean by the Marshallian demand function? Let's just take a minute to look at that. So Marshallian demand function is the demand you have for a certain good X when you have the prices of the two goods varying without altering the income level. So the income level is constant in Marshallian demand. Let me just rephrase that. What we're trying to do is, say suppose you're consuming two goods, X and Y, rice and potatoes, Okay, now we want to know how your demand for, say, one good, say rice, is varying as a function of the price of both the goods, price of rice and price of potatoes, understanding that your income is not varying. Income is constant, which means as prices of the two goods vary, your utility would be varying, right? That's why we have a utility function, because we know that as prices change, your consumption will change, so utility would be varying, but your income is held as constant. And this is like the more common version of the demand function, because most of us don't have our income changing every other day like that, right? In most every day, from one day to the other, from 1 month to the other, our incomes don't really change. We have a fixed budget for things. If we have a certain budget for groceries, it's unlikely that it's just going to change from at a short notice. So that's why Marshallian demand is the one which we mostly refer to. So let's compute this. Last time I did not discuss the Lagrangian method for optimization. So today we will do the Lagrangian instead of the other methods we have used. So let's write the Lagrangian. This is the function we want to maximize. So in your Marshallian demand, we are trying to maximize the utility, and we'll come to Hicksian later. Okay, so let me write this first, Marshallian demand. Okay, so now first let's write a Lagrangian, which is basically just this function which we want to maximize, xy, plus the parameter or variable lambda, and this is your constraint equation. So this is how you write a Lagrangian. Lagrangian is nothing but the function which you want to maximize. In this case, it's the utility function, xy, plus there's a variable or parameter, whatever you want to call it, the Lagrangian multiplier basically, which is lambda, and that is multiplied by the constraint equation such that the constant minus the other variables b minus x px y py is equal to 0. You can just rewrite this in this way, right? B minus x px minus y py is equal to 0. So that is your Lagrangian. So now we take first order conditions. Meaning we take the first order derivative of the Lagrangian. The Lagrangian is the expression which I've written as L with respect to the three variables, which is x, y, and lambda. Lambda is the Lagrange multiplier, but it's a variable. We take it as a variable. So let's write Lx, which is like just the derivative of L with respect to x. This is y minus lambda px, and this is equal to 0. Ly is y minus lambda p y. Wait a minute, sorry. Ly is x minus lambda py is equal to 0, and then we take L with respect to lambda. This just gives you the same expression back again. These are your three equations from the first order conditions. This expression, you can just simplify this expression as lambda is equal to y by px. And similarly, you can simplify this expression to lambda is equal to x by py. And this last expression, you can simplify it as x px plus y py. Now, in this last expression, I just divide the entire equation by px py. So this becomes px py is equal to x plus y. Now, from these two equations, I can just plug in the value of x and y from here in terms of px and py. So this is b px py, and x is nothing but lambda py, and this is nothing but lambda px. sorry, this, we divided the whole equation, right? Where didn't anybody point out? So this just becomes 2 lambda. Let me repeat that. So we divided the whole equation by px, py. So this becomes b by px, py equal to x by py plus y by px, because we're dividing the entire equation by px and py. Right, so we simplify this. Now we know x by py is lambda and y by px is also lambda. So this just becomes 2 lambda. Right? So far so good. So far so good. We can just simplify to the value of lambda here, which is b upon 2px py. So we get an expression of lambda in terms of b, px and py, which is the variables we want to use. Right? Now we have from equation 1 and 2, and let's call this as equation 3. From equation 1 and 2, we can now write expressions for x and y, right? You know the value of lambda, we've simplified lambda. Now we can write expressions for x and y, and this is nothing but, this is the Marshallian demand, because now you're writing x in terms of b, px and py, and that is what the Marshallian demand is, an expression for the demand of a good in terms of budget or income and the prices of the two goods. So let's do that. So we write Marshallian demand as superscript m generally. Like either you write d x, like, you know, if it's demand for good x, superscript m, or you can just write x superscript m. So x superscript m, what was the value of x? Lambda into py. Now lambda is this expression. So this just becomes b upon 2px, py gets cancelled. And you get y, m is, y is what? Lambda into px. Look at equation 1, it's lambda into px. So we plug in the value of lambda again, and again what happens? Px gets cancelled. This is b upon 2 py. So this is your Marshallian demand. You can function, vector, whatever you want to call it. Vector, you can write it like this: xm ym is equal to b by 2px comma b by 2py. So this may look a little bit unlike what we have been doing so far, but once you get this part, the whole theory of income and substitution effects becomes very, very easy. It's, I mean, or at least simpler than what you would be doing without this. Okay, so this is your Marshallian demand function. Now from this, we can now derive the indirect utility function. What is indirect utility function? Indirect utility function is the utility function, but it is not an expression of the quantities of the goods, but rather it is also a function of the budget and prices, just like the in the consumer demand function. So let's do that. Let's write the indirect utility function, because you will be using all of these expressions throughout. So I thought this would be a good recap of all of these things. So u was x, y, right? That was the value of the function u. So now if we write the value of u in terms of xm and xm and ym, the expressions we already got, all we have to do is plug in the value of x and y from this Marshallian demand function we got here. Right? We know the value of xm and ym. Instead of x and y, we just plug in those values. So what do we write here? b upon 2px, b upon 2py. Okay, now we simplify this. This is b square upon 4px and py. So this is your indirect utility function. Okay, next, what can we do from here? Similarly, we can just rearrange the terms to get b as a function of utility and prices instead of utility as a function of budget and prices, which we call as the expenditure function. Okay, now we're not doing anything else, we're just rearranging the terms here, right? So this is b square is equal to 4u px py. And now you take square root on both sides, and instead of b, we just write this as e, and you can write it as a function of px, py, and u bar, you can say, or u, whichever way you want to use it. Let's use u right now. We've not introduced u bar yet. So you just take under root, it becomes what? 2u px py, right? This is just rearranging the terms. This is your expenditure function. So far, all we have done is we have derived the Marshallian demand for the two goods using the two equations we were given. All we were given was the utility function and the budget constraint, right? What we did, we can do the same thing using other methods also. You can do MRS equal to MRT, or you can also do substitute for X or Y or whatever. You'll get the same answer. I just wanted to introduce the Lagrangian method also because we didn't cover it last time. So we wrote a Lagrangian for utility maximization problem, and we solved Lagrangian. We got the value of lambda, which is the Lagrange multiplier, in terms of b, px, and py. And we substituted the value of lambda in the expressions we got for x and y, and we got the final expression for xm and ym, which is the Marshallian demand vectors of the consumer for good x and good y. Then we just plugged in those values of x and y into the utility function to get this indirect utility function. Indirect utility function is where instead of the quantities of the good, we just use the values of the budget and the prices of the goods. Okay. Then we rearrange those terms to get the expenditure function, where we see how the expenditure is varying with utility and prices instead of the other way around. So this is the whole treatment for Marshallian demand. Now we can go to Hicksian demand from here, which is a little different from this. Now Hicksian demand is not complicated per se, but it is slightly less intuitive. That's what a lot of people feel. I mean, even I used to feel that way. But when you study it a lot, it starts to make a little bit of sense. So Hicksian demand is the demand for a particular good holding, holding the utility constant and assuming that their, income can be varying. For example, like, I consume two goods, rice and potatoes, in certain quantity, certain combination, and I get a certain amount of utility with it, right? Now the prices of the two goods change, but I want to stay at that same level of utility. I don't want to change the level of utility I'm at. I don't want to be less happy than I was before. And for that, I will need to rearrange my income. I may need to increase my income, but I'm willing to do that. Or maybe I have some resource for doing that. So in Hicksian demand, what we're trying to see is what happens, how does the consumer demand for something change when prices change and income is also allowed to change, but utility is kept constant. So the application part of it, we will come to in just a little bit. The way we derive the demand is by taking the derivative of this expenditure function. Let me highlight this with respect to the prices. This is your expenditure function. And we take a derivative of this with respect to Px and Py to get the Hicksian demand for X and Y. So X, H, we write superscript H, is nothing but del E by del Px. See, here we are taking Px and Py as variables, not fixed values. That is the part which feels a little unintuitive for many people. But if you start to think of it in terms of a variable, it doesn't seem that weird, right? So you can write EPX or something. Similarly, you can write the expression for Y. Right, you can relabel this as like this. Okay, so Now let's do that. We have the expression for the expenditure. Let's write the Hicksian demand. So this is what? This is 2 under root u p x p y, in which u is not a variable here. I mean, we're not considering u as a function of px or py, right? This is just u. You're holding utility constant because in Hicksian demand. That's why you, if you want, you can write u as u bar, denoting that utility is a constant here. It's not a variable. Okay, so 2 root u is basically a constant. We are 2 root u root py. The whole thing is constant with respect to px. Only variable here is root px, and we differentiate with respect to that. So this becomes 2 root u py, and differential of root px is 1 by 2 root px, right? So this becomes 2 root px. 2 gets cancelled. This is your Hicksian demand. Similarly, you get YH this is the expression you will get. So you can see if this is making sense to you. This should not be very complicated, but I was trying to look for the question. Yeah, so any questions so far? Just in this treatment or just in this theory of Marshallian and Hicksian demand. I know you may think why I'm taking this before, but I will anyways have to explain this later. So once you understand this approach, we will be reusing this approach over and over again in the examples we take. So it's good if you like sort of get it properly now. And I think this part was also covered a little bit fast in the lectures, so I thought I will cover it again in the tutorial. So this is how you derive the Hicksian demand functions. So that's a theory. So coming to the the application part, which is the income effect and substitution effect, that I think I will explain with some example, like with some numbers, because otherwise it's a bit difficult to explain with no values. It's like difficult to visualize. So I will take an example for that, and I will show that in a bit. But any questions so far? No? All right. Okay. So let's go to the first question. Okay, my screen is not updating. Yeah, so this is a question from the book Perloff. I think it's a partially solved example. I don't remember if it's completely solved, but at least some part of it is solved. And I think there is a diagram also there in the book. You could refer to it if you want to. And I took this example so that, if you want to go back and read a little bit about income and substitution effects and everything, you can do that. That explanation is given in the book. So it's something you can read on your own time, because these concepts are a little bit tricky. You do need to spend a little time on them, apart from whatever I'm discussing in the class. And I've taken this example. I will solve it, of course, but there is a lengthier explanation in the book which you could refer to. Okay, so I will give you a few minutes to first attempt it on your own. You have to do the exact same thing what I just did. The only difference is that the function is a little different. You are given the utility function t to the power of 0.4, m to the power of 0.6, where m is live music and t is soundtracks. Okay, and the price of music tracks is 0.5 and live music is 1. Budget is 30. We will come to the price and budget and all these values later. First, you have to derive an expression for the Marshallian demand for t and m, which is exactly what we just did. Okay, so I want to give you some time to attempt it yourself, so you see if it's making sense to you, and then I will solve it. So I'll just mute myself for a few minutes. Please attempt this question yourself. See where you are getting stuck. See what part you are not able to handle, if you are not able to, although you should be able to. Okay, I'm just muting myself for 5 minutes. Please try to solve it and then solve the optimal consumption bundle, and then we will discuss it. Okay. Any luck? Did anybody solve it? Does anybody have the um, expressions for
Yes,
Hicksian and Marshallian demand? Oh, sorry,
yes,
only
ma'am.
Marshallian. Yeah.
Actually, I saw solved the derived expression of Marshallian demand. It answer
Okay.
is 18, and
No, that is the value. That is the consumption bundle. That is not the demand function. Yeah. Okay.
okay.
What did you get as the consumption bundle?
A consumption bundle, I get 25, 18.
It's not 25. You
Uh,
you must have made a mistake.
oh, I
18
have
is
two.
correct. 25 is not correct.
I have two answers, ma'am. Actually, first is 25 and 18, and second is 24 and 18.
No, which one is 25 and 18 and 24 and 18?
Okay, okay.
No, I mean, how do you have two answers? You must have one answer. Now, I'm only asking the first consumption bundle.
I mistake in calculation, I think. Let
Yes.
me
And just
let.
check, there must be a mistake in the calculation. But first, I will derive the Marshallian demand function. I think you joined the class late, so you don't know how to do that.
Yeah,
I
yeah,
will,
yes, ma'am. Yes, ma'am. Yes,
yes.
ma'am. Sorry for
Okay,
the late.
that's okay. So I will just, anybody else, did anyone else try? No? All right, so let's do that. Let's go to question first. Question one. Let me open the question. So you have a utility function which is given by t to the power of zero point 0.4 and m to the power of zero point 0.6. Okay, and you are given the prices. P t is given as zero point 0.5, pm is given as 1, and budget is given as 30, or they say y, so let's use y. Okay, so first, before we compute anything, first let us find the vectors, the expressions for the demand for T and M. So initially, I used the Lagrangian, right? But if you want, I can solve this question without the Lagrangian, because I think we should. I don't know. If you want, I can solve it with Lagrangian or without, whichever you guys prefer.
Ma'am, can you solve with Lagrangian method?
Okay, so if you see the recording, once I've uploaded this, once I finish this, I've already explained Lagrangian method once, but I will solve this using that also, and just for you to understand. Okay, so first, let's write the budget constraint. Budget constraint is TPT plus MPM. Okay, you can call this is the to maximize. This is the objective function, and this is the budget constraint. So we write the Lagrangian, and this is the expression for the Lagrangian. You write the objective function plus lambda, or Lagrange multiplier is lambda, multiplied by the budget constraint rearranged so that the constant minus all the other variables is equal to 0. Okay. Then we take the first order conditions. Lambda, in this case, say t. So in this case, this will be 0.4 t to the power of minus 0.6 to the power of 0.6. So with respect to t, minus lambda pt equal to 0. Then with respect to m, so we are taking partial derivatives with respect to t and m of the Lagrangian function. Okay. Okay, so you get the the third equation is just the budget constraint again. From the first two equations, you can rewrite the value of lambda in terms of these expressions. Let's do that. Let's number these equations. Basically, we want a value of lambda in terms of all the other parameters, okay? So that we can substitute out lambda and we can use the expressions we get subsequently. So we simplify one and we get 0.4. This is from 1, from 2. You do the same kind of thing. We just write it in terms of m by t instead of t by m or something. And divided by pm. Okay, so now we know the expression for lambda in terms of pm and pt and m by t. Now let me look at equation 3 and see how we can substitute that. So we can divide equation 3 by, even if we divide it by pt by pm, we will not see pt. Okay, hang on. Okay, this is a little more complicated using the Lagrange method actually, because the powers are not half, it's 0.4 and 0.6. So, okay, I'm leaving this for now because this Lagrange, I mean, I know it can be solved, but it will take a little bit of just manipulation of the expressions. It's like y is in terms of t, pt, and mpm. And this is in terms of lambda. Yeah, I'll have to think a little bit about how to substitute for lambda because it is not multiplicatively additively separable. So let's do it in the simple way. Let's do the MRS way. That is actually pretty simple. So using MRS instead. I will update this sheet and I will solve the Lagrangian separately, because this is like a complicated expression. If it is just a linear function, it's pretty straightforward, but this is like 0.4, 0.6 powers. So I can't manipulate it like that. Okay, so let's do this. This is pretty simple. This is what ut by um is equal to pt by pm. This is the normal method we use, MRS equal to MRT, right? This is straightforward. So let's calculate ut first instead, which is nothing but del u by del t. What is u? Where is the expression for u? T to the power of 0.4, m to the power of 0.6. So this is um is del u by del m, which becomes, okay, so ut by we just rewrite these expressions, is equal to .4 m by t to the power of 0.6 upon 0.6 m by t to the power of minus 0.4, which if you take to the numerator, it just becomes m by t. So this becomes 0.4 by 0.6 becomes 2 by 3, and m by t points to the power of 0.6 plus to the power of 0.4 becomes just m by t to the power of 1, which is m by t. So this becomes this, right? We rewrite this expression to m by 3t is equal to pt by pm. Now you can write m in terms of t and substitute for that, or t in terms of m and substitute for that, whichever way you prefer. So let's rewrite this. This is M. This is still in terms of T and PT. Now what we need to do is we need to substitute this in the budget constraint. Budget constraint was what? T PT plus M PM is equal to Y. So TPT we leave as it is. M we plug in the value which we've just got from here. Oh, sorry, why am I writing this? 3TPT 1 2 PM into PM is equal to Y. So this PM gets cancelled. You get 2PT TPT plus 3TPT equal to by 2. Sorry. TPT plus 3 TPT by 2 equal to Y, which becomes 5 into TPT by 2 equal to Y. So from here, we need to just rearrange the terms. So we get it in terms of Y and PT. So this is T Marshallian demand, right? That's why superscript M is equal to 2Y by 5 PT. This is the expression. Now you substitute this value into the expression for M and you get the function for Marshallian demand for M. So it's 3 by 2 PT by PM into T, that is the expression for M. Okay, we plug in the value of T here. This 2 gets cancelled. This PT gets cancelled. This gives you 3Y by 5 PM. This is the expression for the Marshallian demand for M. Okay, let me just recap what we just did. So forget about the Lagrange here because the Lagrange is a bit complicated. We can of course solve it and I will solve it and I will upload the solution. But main problem is occurring because this is not in half powers. It is 0.4 and 0.6 powers. But as it happens when we do it using the MRS method instead, we just take ratios and hence that is why it kind of simplifies, right? So here you take UT by UM. This is nothing but MRS equal to MRT. Okay, this is all we are doing here. And instead of plugging in the values of PT and PM like what we do normally for finding the optimal bundle, we leave it there and we substitute the value of M in terms of T or T in terms of M into the budget constraint. Okay, and in the budget constraint, then we just simplify and we rearrange the terms to get T as a function of Y and other prices and M as a function of Y and other prices, whichever it may be. In this case, it so happens that T and M are not varying with the price of the other good. Like you see, T is a function of Y and PT, right? PM is not there in the expression. Similarly, M is a function of Y and PM. It is not varying with the price of the other good. But this may not always be the case. This is just how this particular question has simplified. So this is part of your answer. Okay, let me highlight this. Now we want to solve the optimal consumption bundle. That's not difficult. Now we already have the expressions for T and M. So all we need to do is plug in the values, right? So now can somebody plug in the values and tell me what the optimal consumption will be? Just plug in the values of Y, PT and PM into these expressions. You can write this as T star. This is 2 by 5 Y by PT. Y is 30 and PT is 0.5. 12, and this is 24. That's why I was saying that it can't be 25 because the expression doesn't come out to be like that. So this is 24. M star is 3 by 5 y by pm into y, and pm is 1. So this is 18. Okay, this is your consumption bundle initially. Okay, so now let's go back to the question. We've done part A and part B, right? We've done part A and part B where we derive the expressions for the Marshallian demand and we've derived the optimal consumption bundle. Now we need to find out what happens if the price of soundtracks doubles. Okay, so price of soundtracks was initially 0.5. Now we're saying it doubles, means it becomes 1. And they're asking you to find the income effect and the substitution effect. So what do we do when the price of soundtrack doubles? We know the new price, PT prime, is now 1. So now let's go to part C. Let me label this properly. Okay, so part C, we need to find the new consumption bundle given PT prime is equal to 1 and PM is unchanged, it's already 1. Okay, so now if you want, you can do this whole treatment, whatever we did, we solved the whole thing, we simplified, or you can do whatever you normally do to find the, the optimal consumption bundle. But we know that we've already derived the expressions for T and M, right? You already have the expressions in front of you. Tm is equal to 2y by 5 pt and mm is equal to 3y by 5 pm, right? So from these expressions, we can find the final consumption bundle, the optimal bundle, okay? You don't need to solve the whole thing again. That's why we derive these expressions, right? That's the purpose of having the Marshallian demand function. Marshallian demand gives you the net change in demand, keeping the income constant, which is by default the case. Unless you're told something else, that the income has changed or something like that, we are always going to assume that the income has not changed, right? So that is what the Marshallian expression gives you. So you don't need to do this whole thing all over again. Just plug in the values, and if you plug in the values, you will find in comes out to be 2y by 5 pt prime. Oops. 2 into 30, 5 into 1, right? This is 6. The new consumption of T is 12. That's the final consumption, okay? And what about M? M is not going to change because we've seen that the value of M from this expression, 3y by 5 pm, is only a function of y and pm. It's not varying at all with pt. So even if pt might be changing, we know that m is not going to change, right? So m does not change. So there is no change in m, only change in t. Therefore, the final change for t is 12. Now, there is a second thing we have to find here. We don't just have to find the optimal consumption bundle. We have to find, let me open the question once again. Yeah, you have to find the income effect and the substitution effect, which is the fun part. That is actually the most interesting part of this question, but it kind of comes right in the end. Yeah. Okay, so let's do this. Now, what do we know? Like so far, we know the net effect, we know the new prices, and if we want, we can also compute the initial utility. Let me draw the diagram actually. What happens when we are trying to do income and substitution effects? So that I can explain exactly what we are looking for. Say suppose this is T and this is M. Okay, you you have excuse me, you have a budget constraint initially. This was what T was, what PT was 0.5 and PM was 1, right? So let's say this is the budget. Something like this. Okay, 0.5 and 1. So budget was 30. Let's say this is like 16. This is 30. And we know that this is sort of like a hyperbolic function. It's not like a, this is the part which I have to be a bit careful. Say this is here. I'm sorry, give me a minute. Okay, this is the initial thing, and then I have to redraw this diagram for after the change. So now after the change, what is happening? This budget thing is shifting here, right? This is now 30 because the prices of both are 30. So let me redraw the budget. Let me use some other color. Okay, this is the new budget line. And now the new thing, the new curve is obviously going to be on a different indifference curve, right? This is, I'm just drawing what is happening. I've not talked about anything about Marshallian and Hicksian so far. Now what we are trying to do is we're trying to just map what is actually happening here. So this was the point initially. Now, because this whole part is lost, this part, initially this was all there, but this is now lost because the prices have changed. Now the price of T has increased to 1 also, along with the price of PM. PM has not changed. Both the prices are now 1. So this is, say, suppose the new indifference curve on which the new consumption bundle is falling. This is happening something like this. Okay, not, I mean, it's not an exact diagram, but it's a little kind of like that. Okay, now say suppose I take the same new budget line, the red one, and let me use some other color. I try to draw a line which is sort of parallel to this line. Okay, I don't know how to do this. Something like this, okay? It's a bit difficult to draw, especially on an iPad. But you get the idea, I guess. So there is another point here. It's not exact. Now my diagram is obviously just representative. There's one. So this is the initial. Let me name the points. This is, say, point A, and this is B. Okay. Now when your prices change, you are moving from point A to point B. Okay, this is the net effect we have calculated. T was initially what? 24. Okay. Okay, now my diagram is off because this should have been a little more this side, but let's say this is initial T star and this is new T star value. Okay, and this is sort of, let's assume this is in the same line. It's a bit difficult to do that, but say this is M. It's unchanged. Okay, just let me fix this actually. If you want, you can try to draw the curve. It might help you get a better perspective on what exactly we're doing here. Okay, so this is like this. This is, I think, better. It's not perfect, but still better. Right, so now you can see in this diagram, this is M star. It's not changing. This is T star new, or T star prime. Are you able to follow the diagram, what I've drawn and why I changed it? So in our problem, the value of M has not changed, only the value of T has changed. So I'm trying to draw the two curves such that the initial indifference curve and the final indifference curve fall on the same value of M star, right? Now you see that there is a whole difference between T star and T star prime, which in our case is from 24 to 12. Now there is two components to this, which is what the question is asking you. The question is asking you what? These are the two effects which you are being asked. There's the income effect and the substitution effect. Okay, so this is a substitution effect and this is your income effect. Now, out of these, yeah, I have to keep switching to open the question. Now, out of these, the substitution effect is what we can compute based on the Hicksian demand, or based on just the concepts we have just learned so far about keeping utility constant. Now, if you see from point A to point C, we are on the same indifference curve, right? We know the initial value of utility at point A, and point C, we know the different prices, new price of T and price of M, and we know the original utility value. The budget constraint we don't know because we don't know the value of M, but we know something else. We know utility. So if we can compute, if you can compute this point, intermediate point, you can decompose. What we know is total effect. Total effect is from T star to T star prime. Let me magnify this a little. Okay, this we just computed, right? Initial value 24, final value 12. This we just computed, total effect. But we don't know how to find this breakup of IE and SE, income effect and substitution effect. So we'll calculate the substitution effect, how? Using the value of utility. Now let's do that. Let's say initial utility. U is equal to, what's the expression for U given? It's gone too far up. T to the power of 0.4, M to the power of 0.6. Now let's call this as U bar. We found T to be 24, M to be 18. So let's calculate this. Let me get my calculator. If you want, you can also compute it. We can just check how it's coming out to be. Okay. It's 0.4. This Okay, so we know the initial value of utility, it comes out to be something like 20.195. And we know the new value of new ratio of MRS is equal to MRT. So MR, let's just write the whole thing. MRS is what you, the expression comes out to be for MRS will be the same. Let's say UT by UM. What did we get this before? 2m by 3t. This is 2m by 3t. Now MRT is 1. That is the beauty of it. So this time your MRT is a much simpler expression. So m becomes just 3t by 2. And now what we can do, what do we have to calculate? We have to calculate the value of t, right? Now in the new expression holding utility constant, we have u bar is equal to so again t to the 0.4, and m is what, 3t by 2 to the 0.6. So this is just t into 3 by 2 to the power of 0.6. We know u bar, we know this value we can compute. So we can find the new t value here. You can call this, I don't know what you will call this, t prime. Let's call this t prime because we are computing some intermediate value. If it's not making sense, please let me know. I will explain again. This part is a little weird, so to say. So I won't blame you if you're not getting it. So this gives you t prime comes out to be something like 15.834 or something. So you can approximately take this to be 16. And you can take it as 15.8 blah blah, but the book takes it as 16. So we can just take it as 16. So we know that total effect is equal to income effect plus substitution effect, right? Total effect is minus 12. Income effect, we don't know. Substitution effect is minus 8. You can find the income effect is minus 4. If we take this as 16, total effect we computed as minus 12. Income effect we don't know. Substitution effect is 24 minus 16 is minus 8, or 16 minus 24 is minus 8. Income effect comes out to be minus 4. Okay. Any questions? Do you want me to repeat what we just did? If it's feeling a bit abstract, tell me, I will repeat it. Okay, even though you've not asked, I will still repeat it because I think I can just recap it once again. So all we wanted to do was, after the price change in T, we wanted to compute the new consumption bundle and decompose income and substitution effects, right? Now, as you see in the diagram, let me zoom this. Income and substitution effects together give you the total effect. And when we use if you just find the final and initial optimal bundles and you take the difference, final minus initial, you get the total effect, right? This is the total effect which we get between points A and point B. But we need to decompose it into income effect and substitution effect. Out of these, substitution effect is the one which we can calculate because we know that substitution effect is calculated based on keeping utility constant, right? So if we know the initial values of optimal consumption, we can find out the initial utility level, and using MRS equal to MRT, we can find out the final values of, or you can say intermediate values of consumption at point C, right? This is point C. So this is what we have done now. We found the initial utility level here first, U bar, Then we took the ratio MRS equal to MRT. We found this expression for M in terms of T. We keep utility constant and we plug in the expression for M in terms of T to simplify for the value of T. We know the value of U bar. We plug in all these values, simplify it. I get T prime as approximately equal to 16. Now, total effect is nothing but new optimal value minus initial optimal value, which is minus 12. 12 minus 24 equal to minus 12. Substitution effect is this intermediate value T prime minus initial value, which was 24. So 16 minus 24 is minus 8. And so that is your substitution effect. Income effect is minus 4. So let me just summarize this. Okay, so let's go back to our question bank. Is to learn first question, and generally that is normal. These questions are a bit long and they do require a lot of computation. So, but I do want to take these examples because this is an important part of consumer theory. Okay, if you're able to do all this, then the questions you have in your assignment and stuff like that, they will be pretty simple. You will not have a problem. Okay, so the question 2 is a simpler question compared with question 1. You are given that Charlie consumes apples and bananas, and his utility is XA, XB, where price of apples is 1 and price of bananas is 2, and his income is 40. Okay, very similar kind of a question. So you have to find out how many apples and bananas Charlie will consume. And then if the price of bananas falls to 1, how many apples and bananas does he consume now? And in this example, which effect is dominant? Like you need to decompose income and substitution effects again and find which effect is dominant in this example. Okay, so I'm not solving this question because it is very similar and easier than the question which we have just solved. But I will upload the solutions for this also, but I do want to give you guys time to solve it on your own. Okay, I want you to attempt this on your own. So for this class, I will upload the solutions by tomorrow, not today. I usually upload everything the same day, but these solutions I will upload by tomorrow because I want to give you at least a day to attempt it on your own. Okay, let's go to a different kind of question. Now you have a consumer whose utility is given as U is equal to X plus Y. And income of the consumer is 10 units. The price of X is 2, price of Y is 3. So now we see that there is an increase in price of X, and now the new price of X is 4. So now you're asked, what is the Marshallian demand vector after the price increase for good X? And what is the Hicksian demand vector for the after the price increase? So I want to give you a few minutes to think over it. This is different from previous questions. Obviously, concepts are going to be the same, but the form of the utility function is different. Okay, so I'll take a break of 5 minutes here again and try to solve it, apply whatever we have learned till now, and see if you can find the answer or solve the question, and then we will solve it together. Okay, so let's see what the question is saying. U is given as x plus y, right? It means that it's a case of perfect substitutes, right? It's not like what we had before, u equal to x into y. It's a case of perfect substitutes. So let's write this down. Open the question again. Oops. This is what is given to you. Okay, this is fairly simple, at least so far it is pretty simple. Let's just, before we consider price changes, all of that, first let's just see what is exactly happening here. Okay, here we see, let's write the budget equation. Okay, this is the budget equation, and MRT is equal to px by py. Sorry, I'm having the strepsils. It's just I'm coughing too much, so I can't speak otherwise. This is equal to 2 by 3. Okay. Now let's see MRS. MRS is equal to what? It's 1. MRS is 1 because the coefficient of x and y both is 1. Right? So MRS is going to be 1. Therefore, MRT is less than MRS. So what is going to happen? What does that mean? That price of x is much lesser than the price of y, comparatively speaking, but the consumer prefers x and y equally. It doesn't matter to the consumer whether he's consuming x or he's consuming y. That is the point which we need to understand in the case of perfect substitutes, especially in this case where you have u equal to x plus y. There are no coefficients to consider, right? I mean, even if you had coefficients, you would just compute the MRS. But in this case, I mean to say that that is like immediately obvious that it's like apples and bananas. You don't care if you're eating an apple or if you're eating a banana, right? So in this case, because he doesn't care whether he's consuming one or the other, and the price of one good is lesser than the other, what is he going to do? He's going to consume entirely that one good, which is which is cheaper, right? So what is going to happen? Therefore, he consumes only good x and no good y. Right? MRT is what? Px by py, which is less than MRS. Therefore, he's going to consume only x, right? What is the budget thing? X px plus y py. Now, in this, plug in the value of px, which is 2 plus 0 is equal to 10. Therefore, x is equal to 5. Right? So, therefore, initial consumption is it's 5 comma 0. Okay, so far all we have done is we have just found what is happening in the initial case before the price changes, etc., and what is what is the initial consumption. So initially consumer is consuming sorry, good x in entirety. Okay, so now we have a change in price. Now we compute new MRS. MRT is same. Oh, sorry, this is new MRT, not MRS. MRS is same, equal to 1. Now you have one MRT is greater than MRS, or price of X is greater than price of Y. Therefore, consumer will consume only good Y and no good X. This is the main thing which you have to which you had to reason out. That is the only important thing to be understood in this question, actually. So the whole Marshallian and Hicksian demand, we will come to that, but the main concept to be understood is that once the price of good X changes and it increases, now the ratio of prices between X and Y has flipped. So now, because the consumer is absolutely indifferent between consuming X or Y, he is now going to switch to the good which is cheaper. And if you think about it, that's what we do, right? If there are two products in the market, say Nescafe and Brew, and there are two coffee sachets, if I absolutely don't care which one I'm drinking, if I like both equally, I will consume the good which is cheaper in entirety. I will not consume the other at all, right? And if the price changes, if say suppose Nescafe decides to reduce its prices, I will switch to Nescafe instead of consuming the other one, right? That's all that's happening. It's pretty intuitive if you think about it. Now the question is asking us something different, right? It's asking us Marshallian consumption or Marshallian demand. For Marshallian demand, the golden rule is for Marshallian demand, we keep income constant, right? Therefore, income constant. So what is going to happen when income is kept constant? Income is still X. Income is still 10. Income was given as 10. Let me write the budget equation again. Now you have Px prime is equal to 4. Py was what? 3, I think. 3. And budget was 10. Now, we know that in the after price change, he's using only Y. He's not consuming X at all. So X becomes 0. So this becomes 10 is equal to 3Y. Therefore, Y is equal to 10 by 3 in the in the Marshallian case. Okay, Marshallian means we are taking income constant. This is what the question is asking you. Now we take the Hicksian case, Hicksian demand. Hicksian demand means taking utility constant. What was the initial utility? U is X plus Y. Initial consumption was 5, 0. Therefore, you can write U bar X plus Y is equal to 5. This is the utility we initially had. Now, after price changes, the question is saying you need to find Hicksian demand, meaning you need to hold utility constant. So after price changes, we assume the budget is flexible. He can get some other funds from somewhere to maintain his utility level. And he's still going to consume Y in entirety and no X. Therefore, after price change, U bar is equal to 0 plus Y equal to 5. Therefore, Y prime is equal to 5. This is your Hicksian demand. X is 0. Therefore, you can say Xm Ym is equal to 0, 10 by 3 and Xh Yh is equal to 0, 5. I put it as subscript. You can put it as superscript if you want. It means the same thing. Okay, this is what the question was asking you, and this is what we found. Okay, is this good? Okay, now in the next question you are given is variant question 8.6. My screen is not shifting. Yeah. The demand function for good X is given as a function of Px, Py, and M. And this is given as an expression 2m by 5px. The income is known to be 1000, price of X is 5, price of Y is 20. Okay, my typing has gone off the rails here. So let's just assume I've typed. I'll fix this typo. If the price of X falls to 4, then his demand for X will change from what to what. And this is pretty straightforward here. You have all the values of X given. Of the values of M and Px given. So you just straightforward compute the value of X. Initial value of X is 2m by 5px. 2m means 2 into 1000 by 5 into x. Px is 5. 2000 by 25, whatever that comes out to be. 2000 by 25, 880, sorry. 80. So initially it is 80. Now the price of X is falling to 4. 2000 by 5 into 4, 20. So that is 100. So his demand of X will change from 80 to 100. This is straightforward, right? I've just done the calculations just verbally. I've not explained because this is straightforward. Next question. If his income were to change at the same time so that he could exactly afford his old commodity bundle, what would his new income be? And what would be his demand for X at his new level of income and prices Px and Py as given? So now what we are asked is if his income were to change at the same time. Actually, I've not solved this question, so I'm also encountering this question for the first time. I just copied it. His old commodity. Okay, so now I think we'll have to, there is something more to this question which I have probably missed because we are missing a utility function. And I think there should be a utility function, otherwise we cannot compute the old one. No, actually, oh, this is straightforward. So you are just saying that, original consumption was what? Original consumption was 80 and the original income was 1000. Wait, let me just write this down. Can't be done verbally. Let me open the question. So this is just a little bit of practice of whatever we have already learned. We are given X as a function of Px, Py, and M as 2m by 5px. Okay. Initially, M is 1000, Px is equal to 5. Then price of X changes to 4. Okay. Now, initially, X is equal to 2 into 1000 by 5 into 5. It's equal to 80. Now, part A is asking us that if the income were to change, M changes to M prime, so that he could exactly afford his old commodity bundle, what would be his new income? So now we just know initial consumption, we just flip the whole expression. We write X prime is equal, sorry, X, not X prime, X is equal to 2M prime by 5px prime, right? Because M and px have changed. So X we know, we calculate this 80. We plug in the value of 80 here, 2m prime by 5 into 4. Just solve for m prime. This is 80 into 5 into 4, 20. This is 1600 by 2. Or let me write this. 10. This is 800. We are just saying that, at what income level would he have exactly the same consumption as before. Okay. This is actually just arithmetic. Just plug in the values and you solve for the expression. Let's go back to the question. The question is asking the second part. Substitution effect is change in demand from this to this. Income effect of price change is the change in demand from this to this. Substitution effect is what? When we are holding utility constant, right? So substitution effect in this particular case will be, let me also see, we're not given the utility. So we know the income change part. So yeah, so what we computed in part A is substitution effect, because we are saying that he is changing his income so that his utility is remaining constant. So we are basically changing the income to keep X constant. No, we've not given utility constant. We're only given X constant. Okay, I'll have to check the question. I think there is something missing because I think utility function or relation is not given here. So the total effect is going to be whatever we computed in the first part. X will change from 80 to 100. Substitution effect, how do we find this? So, okay, the total effect is from 80 to 100, right? Right. So, okay, part B, I will have to check a little bit because I haven't solved this question before. I just added it to the slides. And I didn't get the time to solve it. Part B, I will think over it, and maybe there is a part missing. Okay, I may have just missed it in a hurry or something. So there's a possibility that part B is incomplete. I will check it and I will update the slides if there is some mistake. Okay, this is probably going to be the last question, although I have added another one. So in case we are not able to finish both the questions, I would encourage you to please solve it on your own. And if you're not able to, I will discuss it in the next class. Let's do this part at least. So you are given that a daily commuter sees bus tickets and metro tickets as perfect substitutes, okay? X and Y. And his utility function is X plus 2Y. Price of X and Y are given 3 and 5. And his budget is given as 30. So firstly, we find the optimal consumption bundle that I think you can all do. Now, after the new budget, the prices of both goods change such that Px is equal to 4 and Py equal to 8, whereas his income remains the same. So now we need to find a new consumption bundle. So this question is very much like the question which we just did, right? What will we do in this question? Does anybody want to attempt? I think I'll mute myself for a few minutes. I want you to attempt this because this is very much like this question we did. Question 3. So in this, what did we do? We compared MRS with MRT, and then we saw which good is going to be consumed. This question is very similar to that. And okay, my screen is not updating. Right. So part A and part B are just a recap of that same concept in a way. In the part C, we will find the new optimal consumption bundle, and we will decompose income and substitution effect. So part A and part B, I'll solve part A. Part B, I will leave it to you. You can solve this. It's pretty simple. And then I will do part C. Okay, let's go to Okay, let's write the budget equation. Okay, so this is 3x plus 5y is equal to 30. Let's compute the MRS is equal to UX. Let me write the proper X. This is MRS. MRT is PX by PY. Price of X is 3 by 5. So what do we see? Which expression is bigger? This is, you can write this as 0.6. You can write this as 0.5. Therefore, MRT is greater than MRS, right? So he is going to consume only good Y, because price of X, see what we're trying to do when we compare MRS and MRT is we're trying to see how much marginal utility he's getting from consumption of X versus consumption of Y, versus how much each additional unit of X is costing him compared with each additional unit of Y. That is what we're trying to compare. Like what we call bang for the buck, right? UX, how marginal utility per price of the good, of both the goods, marginal utility of X per price of X, marginal utility of Y per price of Y, which is better for him. So in this case, we see that the marginal utility of Y per price of Y is better, because PX by PY is 0.6, whereas UX by UY is 0.5. Means the price of X is higher relative to Y, and that ratio is basically greater than the utility, marginal utility values. So he's going to consume only Y. He's going to consume okay. So only Y. So X is 0. Therefore, 5Y is equal to 13. Y is equal to 6. This is your initial consumption bundle, which is what we had to compute. Now, in part C, this was part A. Part C, we are saying that Px prime is equal to 2. Therefore, new MRT is what? Px prime by Py 2 by 5, right? Yes. Our S is still equal to 0.5. This is 0.4. So therefore, now what is going to happen? Now he's switching to wood X. And no Y, right? Entirely, I'm just writing entirely, meaning he's not going to consume Y at all, because now he's seeing that he's getting a better value for his money from consuming X. So now we can just redo this whole thing. 2X plus 0 is equal to 30. X is equal to 15. Therefore, new bundle is equal to X prime star Y prime star is equal to 15, comma 0. Okay, so far so good. This is, I've just sort of captured the same thing. Let me find the question again. Give me a minute. I'm just trying to see if I have missed something. Okay, so this is our final consumption bundle. Initially, what did we have? We had 0, 6. Now we have 15, 0, right? Now, what we want to do is we want to decompose this into substitution and income effect. So how do we do this? As usual, we find the utility before price change. Just give me a minute. Have I taken some wrong values or something? No. It was, oh, I think I've taken some wrong value. Ah, shoot. Just, sorry, let me open the question again. Yeah, I've done it correctly. Sorry, I thought I've taken something wrong. No, it's correct. So yeah, let's go back to what our initial consumption was, 0, 6. So this is 0 plus 2 into 6. This is 12, right? Now in the new after change, keeping utility constant, we get u bar is equal to x prime plus 2y prime. U bar is equal to 12 is equal to, what did we get? 15. Oh, hang on. Yeah, so here we are trying to find x prime, meaning that intermediate value, not the initial value. X prime plus, we know that this part is 0. So this was what? 12 is equal to x prime, or you can just put double prime, even though this is not a derivative, but okay, I'm just trying to differentiate it from what we've just calculated. Just say x bar. X bar is equal to 12. So what is happening to the consumption of x? Initially it was 0, right? Then it goes on to being 15. And in between, it is going to 12. Now, what we wanted to compute was the income effect versus substitution effect, right? So substitution effect is equal to 12 minus 0 is equal to 12. Total effect is equal to 15 minus 0 is equal to 15. Income effect is therefore 3. Let me explain what I've just done in case. So what we did, let me recap this. We knew the original consumption bundle. We knew initially the consumer was consuming only Y, no X, right? Because we had price of X, relative price of X versus Y and relative marginal utility. We compared MRS, MRT. We found MRT to be higher, and therefore we assumed, or we interpreted that the consumer is going to consume only Y, no X, right? So if you put X equal to 0 and you solve the budget equation, you get Y is equal to 6. Initial consumption was X star Y star equal to 0, 6. Okay. Then we see that the price of X has now fallen to 2. And we compute the new MRT, which is now 0.4. MRS is obviously the same because utility function is the same. And now we see that MRT is less than MRS, right? Therefore, he is going to consume entirely X. He does not consume Y at all. So now his new consumption of X is, we just plug in the values of Px prime and we know Y is equal to 0. So 2X equal to 30 because the budget is still the same. So X comes out to be 15. The new bundle which is the final consumption bundle, is 15, 0. Okay. Now we need to find income and substitution effects. So we can find substitution effect in a pretty straightforward way, which is that we take utility constant, and for that purpose we compute the initial utility. Initial utility, say u bar, was x plus 2y. This is the initial part. X was initially 0, y was initially 6, we get the value 12. Now after price change, we keep the utility constant and we compute the intervening price of quantity of X, which he's consuming in between, holding utility constant, right? Which I'm calling as X bar. So we know Y is still going to be 0 in the final case because we know he's going to switch to X. So we get very simply the value of X bar equal to 12. So the final result is that the consumption of X changes from 0 to 15. And the substitution effect is that value 12 minus initial, which is 0, which is 12. Total effect we know is 15 minus 0. So income effect becomes 3. Okay, this is the end of the discussion. So is this clear or any questions? We'll keep, this is a concept which will keep recurring again and again in this particular chapter at least. From the next week, we will do producer theory, so you will not be hassled with this, but this is an important concept. Let me go to the questions. There is another question on this, but I'm not going to solve this because this is relatively simple after all the discussion. It's not the same as a perfect substitute case. Okay, the utility function is different. It's x plus log y. So be careful. You can't just directly assume that he'll consume only one of the other. This is a quasi-linear utility. But in this, we are discussing same kind of concepts. Okay. So I will ask you to please solve this because I anyways need more than 10-15 minutes to solve this and explain this properly. And if you have trouble, I will solve this in the beginning of the next class. Okay. Any other questions, problems?
Madam, I did not get how we got substitution effect equal to 12 minus 0 and total effect equal to 0.
Because Hicksian demand gives you the substitution effect. Hicksian demand is what? Hicksian demand is when you compute the consumption bundles keeping utility constant. You remember this diagram? This diagram. So in this case, the curves are different. So diagram, I mean, it will not be exactly this, but if this arrow where I've made this part, right? This point C, we're trying to compute the value of consumption of the two goods at this point, intervening point C, where you're holding utility constant. Because you can't compute substitution or income effects in any other way. Substitution effect is when you are compensating the consumer for his income or you're altering his income, but you're keeping utility constant. We know the initial utility, we know the MRS and MRT, and we use those conditions to solve for values of X and Y at point C, the intermediate point. And we take the difference between C and A to compute the substitution effect. The remainder is the income effect. Okay?
Okay, madam.
Yeah, so in this, it's a case of perfect substitutes. So our calculation is much simpler because initially X was not being consumed at all, and afterwards it is being consumed. So the calculation is a bit straightforward. It's not that complex. But the diagram, I mean, of course, it's going to be different, but conceptually, that is what we're doing. Okay. All right. So please go through this concept, read the books. I have given 2-3 books for reference, which you can refer to. All of these books are pretty decent for that purpose. And they have some examples. Please go through the examples and please solve this question 6. And if you have any trouble with it, I will, of course, solve it in the next class. But do try it on your own once so you know how much you're getting the concepts. Okay. All right. So then I'll end the class here and I will see you all next week. And next week I know is the day after Holi, but we will have a class. So just wanted to mention that. All right. Happy Holi, everyone. And I'll see you next week.